Hi everybody and welcome to our next live lecture. So in this week we're going to cover sections 2.4, 2.5, and 2.6. They talk about the topics symmetry, transformation, variations, and then there's some applications too along the way. So let's start with symmetry. Symmetry basically is a mirror image of something, and it often occurs in nature or in art. If you think about the body of a butterfly, for instance, it's a mirror image from one side to the other. Even if you look at our own faces, for instance, they're not perfect, but they're pretty symmetrical, right? It's pretty much the same on the left side as the right side, for instance, right? So we do have symmetry a lot. And what we're going to talk about today would be symmetry with graphs and with equations. There are lots of different kinds of symmetry. We're going to talk about three specific ones, but there are other symmetry cases out there as well. So just keep that in mind if you're going through. The first one we're going to look at is symmetry with the y-axis. I'm going to get three different colors out just to talk about this. So symmetry with the y-axis, the graph is a mirror image over the y-axis. We can see this graphically, and I'll show you an example in just a minute. And we can also see this algebraically by replacing x with negative x to see if we get the same or an equivalent equation back out. So I'm going to kind of bop back and forth and show you an example while I go through the different kinds of symmetry. So here's an example of the first one. Right, here is my y-axis, and this one is symmetric with the y-axis. Sometimes we'll say symmetric with respect to the y-axis, and that means the same thing. But what you want to notice visually is that this is a mirror image over the y-axis. So if I were to fold my paper in half right along that y-axis, those two sides would touch. We can also see this algebraically. So here is the example, and we can see it because if we let x be negative x instead, plug it in, and simplify, what happens is we get the original equation back out. All right, so here's our equation. What I'm going to do instead of using x, I'm going to plug in negative x. Now what happens though is that negative x squared is negative x times negative x. So those negatives end up canceling out, and what happens is you revert back to the original equation. So this is what happens algebraically when we have symmetry with the y-axis. So you can see it physically, right? So you can see the actual visual of that, and then you can also see what's happening with the equation. And what you notice on the points, for instance, so here's one point. This is the point 2, 3, and here's the point negative 2, 3. And what you're noticing is that the y value is the same even though we have a positive or negative x. And that's basically what this is saying here, is it doesn't matter if x is positive or negative, you're going to get the same output. So that's why they both have the same y value, even though they have opposite x values. The next one I want to look at is symmetry with the x-axis. So you're going to see symmetry with the x-axis instead. And algebraically, you'll notice that we replace the y with negative y, and again, we get the same equation back out. So an example of that is on your next page, and it's this one here. So here is our x-axis. And you can see the symmetry, right? If I were to fold my paper right along that x-axis, those two pieces of the graph would touch. They're mirror images over the x-axis. So what we're going to do here instead of the x's, we're going to replace y with negative y, plug it in, and simplify. And what's going to happen is we will get the original equation back out. So you have the same sort of idea here. Here's my equation. So I'm going to replace the y with negative y instead. And this example is actually pretty similar to the last one. When you square, that negative gets canceled, and you get the original equation back out. When I look at the graph, for instance, so here is the point 0, 2, and here is the point 0, negative 2. So what's happening in this case is that the y value, whether it's positive or negative, gives you the same x value. So it's the other direction compared to the last example here. So, you know, and again, you can do other examples here too. So you could look at negative 5, 3, and this is negative 5, negative 3. So you're getting the same x value for both the positive and negative version of the y value. All right, and the last one I want to show you is symmetry with the origin. So this is the hardest one to see, I think. It almost looks like the graph does a double flip, so that it kind of rotates around the y-axis and the x-axis. You can also think of it as a 180-degree rotation here if you're good with rotation, so a half circle turn. And algebraically, you replace both x and y with their negatives, and you'll get the original equation back out. So the example that's pretty classic for this one is x cubed, so y equals x cubed. So this is going to be symmetric with the origin. And what I want you to notice is the graph almost looks like a double flip in a sense. So if I take the right side of the graph here, if I were to flip it first over the y-axis, and then I would also flip it over the x-axis, I do see that those two halves would now match up. So you almost have like a double folding of your paper here. Another way you could think of it is that it is a half circle turn. So 180 degrees is half a circle. So you're taking this and you're kind of doing a half turn there. And you get the same graph back out. Algebraically, what you're going to do is you're going to replace x and y with negative x and negative y. So you do both of them. You're going to plug that in, and of course you're going to simplify, and you'll get the original equation back out. All right, so here's my example. I'm going to replace them both, so negative y and then negative x. Now, negative x cubed would have 3 negatives. So what happens is 2 of them cancel, right? But the third one is going to stay, so you end up with negative x cubed here. And then I could clean this up a little bit more by dividing both sides by negative 1, and I do get y equals x cubed. So after I do a little bit of simplifying, again, I get that original equation back out. So here we're negating both parts. Now, how do you test an equation for symmetry? We do it individually. So the interesting thing is that equations can have none of these symmetries. They could have all of them. They could have one of them, and so on. So you do really have to test them all individually here. And of course, there's other symmetries as well. So we're just testing for these 3. So let's go through. Let's test for, what do we do first? The y-axis. So for this one, remember we plug in negative x. So I take my equation, I plug in negative x here. When I square that negative, it does become positive again, and I do get the original equation back out. So there is symmetry with the y-axis. The next one we tested for was the x-axis. So to test for x-axis symmetry, we plug in negative y. Now, when you have 4 negatives to the 4th power, they're all going to cancel out. So you do get back the original equation here. So we have symmetry with the x-axis as well. And then I test for the origin. So in that case, we're going to plug in negative x and negative y. Oops. And I'm going to get negative x squared plus negative y to the 4th. Now we've already seen that this becomes x squared and this becomes y to the 4th. So again, we get the original equation back out. So I do have symmetry with respect to the origin as well. So this particular example has 3 kinds of symmetry. Again, some of them may have none of these types. Some may have just 1 or 2. So you really need to make sure you're careful and you check them all individually. I don't have a shortcut there to say, oh, if this one works, you don't have to check the others. You do want to check them all. The other thing you can do, and I'm going to bring up my phone real quick with you guys, is you could use Desmos to check your answers too here. So let me just darken my screen a little bit. Makes it a little bit easier to see. And I'm going to type in that equation. So it's x squared plus y to the 4th equals 5. And when I graph that, I get this kind of not quite oval shape, but a little bit like an oval. And you see that it does actually have these symmetries. It's symmetric with the y-axis, right? I have a left to right mirror imaging. It's symmetric with the x-axis because I have an up and down mirror imaging. And it is symmetric with the origin. If I were to kind of double fold, the 2 diagonals would match up. So it does have symmetry. So it's always nice to graph and double check your work as well. But you do want to make sure you know how to do it in both directions, both with the algebra and with the graphing. Now we say that a function is functions that are symmetric with the y-axis, we do call those even functions. And functions that are symmetric with the origin, we call odd. Now, something to note, there are no functions that are symmetric with the x-axis, because when you have something like this, it would fail the vertical line test. So that's why we don't have a special name for that one. So for functions that are symmetric with the y-axis, we'll call them even functions. And for the origin, we call them odd functions. So let me show you that notation as well. All right, so we're going to determine if the function is even, odd, or neither here. All right, so if a function is even, so how are we going to test for even? What you do here is you just plug in negative x, and again, you see if you get the original function. So the function that we're working with is this one here. I know it's a little hard to read. This is a little 7 as well. So I'm going to plug in negative x. So I replace x with negative x. And then I'm going to go ahead and simplify. Now, because I have a power of 7 here, I will have an extra negative left over. Same thing for the cube as well. So this becomes 5 negative x to the 7th minus 6 negative x cubed minus 2 times negative x. And then working with these negatives, it becomes negative 5x to the 7th plus 6x cubed plus 2x. So once it's simplified, you want to see, do you get the original function? And we don't, right? It's similar, but the signs have changed. So this is not the original function, right? So this is not the original. So it is not even. The notation for even functions look like this. So we're checking to see if when we plug in negative x, we get the original. So this is what they're referring to in that notation as the original. So in this case, this is not happening here. So this is not an even function. Now for odd, again, you plug in negative x here, but you're going to see if you get the opposite function. By opposite, I mean that all signs are going to change. So what you're looking for here is when you plug in a negative x, do you get the opposite function? Right? So all those signs are going to change over. Now, we've already done this, right? I know what the negative looks like. What does it look like if I change all the signs over? So the first one will become negative, then positive, and then positive. So is that what we had happen here? Yes, right? All those signs changed over. So we did get the opposite, right? So we're seeing here that when I plugged in a negative, I got the opposite of all those signs. So this is in fact an odd function. It is the same definition of symmetric with the origin. It's just that remember for symmetry with the origin, we had both the x and the y were negative. So that's actually what we're showing here. When the x is negative, the output is negative as well. That sign changes. So it's the same idea as symmetric with the origin. It's just written a little bit differently. If you have neither of these cases, then we actually just say that it's neither. So for instance, if f of x equals x cubed plus 2, for instance, and I plug in a negative x there, and I simplify, I would notice that this is not the same, right? It's not the original because my first sign changed over. So it's not even. But it's also not the opposite because not all signs changed. The first one did, but the second one didn't, right? The 2 stayed positive. So it's also not odd. So something like this, we just call neither. So it's neither even nor odd. We don't give it a special name otherwise to that. All right, so that's the end of symmetry. And of course, there's more examples in your text that you can see. The other thing I want to talk about with you guys on the next topic is transformations. This is a big topic as well. So to start here, I have a little quick link citation, well, not a full citation, but a link at the bottom here, is these are some basic graphs that you should already be familiar with. And again, this is one, I know it's hard to see on the screen, so you may want to go ahead and just download this. It's posted for you guys in Blackboard. But these are functions that you should be pretty familiar with already. So here you have your basic square function, x squared. Here you have your basic cube function, x cubed. Your absolute value function. This is your identity, so just your basic line through the origin. Your square root function, your cubed root function, and then the reciprocal. We're going to be dealing probably mostly with the first, probably the first 5 or maybe 5 or 6. So we'll get used to these. And as we go through them too, you may want to keep a little running note for yourself of some of the points that you're using. And I'll show you examples as we go through where, if you use this one, make a little note here of what the points are so you don't have to keep finding the same points over and over again. They do have your domain and ranges here provided for you as well. But it's going to be helpful to have a table of points for each of these functions. So transformations are basically taking functions that we're already pretty familiar with and tweaking them. So maybe the shape stays the same, but we shift it up a little bit, or we flip it around the x-axis, or we stretch it or compress it or something like that. So those are called transformations, and there are different types, but the 3 that we're going to look at are going to be as follows. So the first one is a vertical or horizontal translation. That's the formal name. I'll usually just say shift. Every transformation can go vertically or horizontally. So remember, vertical is really like in an up and down direction. Horizontal is in a left to right direction. Now, these types of transformations happen whenever you see addition or subtraction in the change to the function. So I'm going to show you some examples so that hopefully it makes more sense. Now, your vertical changes tend to be pretty straightforward or a little bit more natural. So if you take your original function and you add a value to it, it's going to shift the original function up. Or if you take your original function and you subtract a value with it, it's going to shift it down. So these are both outside changes to the function because we're just adding or subtracting a number kind of like after the fact, right? It's not being plugged in or anything like that. Changes that are horizontal tend to be a little bit more difficult. They're backwards to what we usually expect of them. So when you add a value, you end up shifting to the left. And when you subtract, you actually end up shifting to the right. And actually, this has to do with our discussion this week. These changes are always inside changes because you're basically plugging something in to the function. So it's not just hanging around on the outside, but you're actually plugging it inside the function. So it's in parentheses, it's in a denominator, it's in a root, it's in the absolute value symbols, etc. So it's inside. Those inside changes are always horizontal. So let's look at a couple examples here. So in each case, we're going to identify the parent function. The parent function is sort of the starting function or the base function that you should be familiar with already. So in this example here, I'm just going to use fn for function. The parent function would be just x squared. So usually it's a function that you're already pretty familiar with. So what we do is we graph that parent function first. And I'm just going to plug in a few points here. You don't need a ton, just enough to get the pattern. So when I plug in -2 and square that, I do get 4. -1 squared is 1. 0 squared is 0. 1 squared is 1, and 2 squared is also 4. So when I graph this parent function, it looks like this. Now this is what I'm saying now we just graphed the parent function for x squared. So what you may want to do is either make a little note card for yourself or go back to this sheet here and fill in that table. I mean, it doesn't take too long to find these values, but it's nice because once you have them done, you can just reuse them over and over again and not have to redo all that work. So you may want to kind of keep a running list for yourself. Now I'm going to go ahead and do the other function. So what you're looking at is, well, how did it change, right? It went from x squared, but then I subtracted 6 with it. Notice how 6 is just kind of hanging outside the x squared. It's not in parentheses or anything like that. So this is an outside change. And if I go up to the top here and I kind of look and say, okay, well, this looks like this, right? It's an outside change. I'm subtracting it. So what do? I shift down that many units. So I'm going to shift everything down 6 units here. And I use 6 because the number here is 6. And I can just count. So I can take each of these points and just count down 6 units. And same thing on the other side. And the shape is going to stay the same. So again, the point is that we kind of already know the base shape. So instead of doing a whole bunch of extra work, I can just apply that change. Now, if you want to make a new table, you can. Usually for shifts, I tend not to because they're pretty quick, but you can. So in this case, think about it. If you're going down 6 units, for this particular case, that means that all the y values get subtracted with 6. So if you want to make a new table, you always can. Here I have another example. So our parent function in this case is just going to be the regular square root function without the +2. So it's just your base function. And again, you may want to start by making that table. Now, plug in values that make your life easy. So if I plug in 0, the square root of 0 is just 0. If I plug in 1, the square root of 1 is 1. Now, if I plug in 2, that's going to be kind of hard, right? Square root of 2 is not a whole number. But if I plug in 4, the square root of 4 is 2. And if I plug in 9, the square root of 9 is 3. Now, I cannot plug in negatives here because those will give me imaginary numbers. So my graph looks like this. And again, I'm just using 2 different colors here to help show the different processes. in the different functions. And again, now take this and write it on the last page, or keep it on a note card so you have these base functions all ready to go. And then I'm going to go and take a look and see, well, what happened? I do see a change here of +2. Notice that the change is inside the root, right? It's underneath the root. It's on the inside. So this is an inside change. So it looks like this, right? We're plugging it into something. So a +2 is a shift to the left. So we're going to go ahead and take everything and go 2 units to the left. And again, I'm just going to count. So I'm going to take this point and count 2 spots left, 2 spots left, left, and left. And I'm just going to go ahead and keep that same general shape. If you want to make the change here, right, we're going left 2 units. So think about what's happening. All those x values are going smaller, but the y values are staying the same. So all your x's basically get subtracted by 2 for this particular problem. So again, I don't usually make new tables for the shifts. They tend to be pretty straightforward, but you can if you find it helpful. So you have to just think about, well, what would happen to my values? Right here, the x's stay the same, but the y's changed. Here, the y's stay the same, but the x's changed. All right, my next type of change here is called a reflection. And a reflection is basically just a flip. Notice again that we have 2 things, right? See how this is an outside change, whereas this one is on the inside. So remember, outside changes are always affecting things in an up and down direction, and inside changes always affect things in a left to right direction. So when you multiply the entire function by a negative, you get this flip in a down up direction. When the negative is on the inside of something, then you have a flip left to right. So here we have that same parent function from the page before. And again, it does help to just have that written out. So I'm just going to leave it in red. So let's see, I had 0, 0, 1, 1, 4, 2, and 9, 3 as my base function. So I start with that parent function. And then you want to, actually, I'm going to do it over here too because we have the same parent function here, right? Right, so same parent function for both of these because they're both just the square root function. Now think about your differences. Here, see how this negative is outside the root? This is an outside change. So outside changes are always up and down. So we're going to end up flipping this from up to down. So you're just going to mirror over that x-axis. So the 0, 0 stays the same, but this one comes down 1. Here I'm going down 2, and here I'm going down 3. So I'm just counting the same number of spaces. Now, if you like to, you can also update, again, your table. So think about what's happening here. The x values aren't changing, but all the y values are becoming their opposite. So when you have an outside negative, you're basically just multiplying all your y's by -1. So if you wanted to redo that table here, your x's didn't change, but your y's all became negative. For this one, notice that that negative is on the inside. So an inside change is always a left to right change. So we're going to flip in a left to right direction. So if it's on the right, it's going to flip to the left. So again, I'm just going to mirror it. 1 spot over, 1 spot left. 4 spots over, 1, 2, 3, 4, 4 spots left. 9 spots over, 9 spots left. So I'm going to go ahead and just make that change. Now again, think about what's happening here. So when the change is a negative on the inside, well, what happened? All your y's stayed the same, but the x's became the opposite. So you can multiply your x's by -1 to get the new table, again, if you find it helpful. So I go back to the original. My x's now become negative, but the y's stayed the same. So it's really important to notice if your changes are outside or inside, because that's going to affect how they're moving. Are they moving up and down? Or are they moving left to right? So you want to really pay attention there. The last type of transformation we're going to look at is a shrink or a compression. And this one I think is the hardest one because it's usually using a multiplier. So the other ones you can do a bit more visually. This one I usually like to write a table out for. So you see these when you have some sort of multiplication or division. Actually, I should note too, for the reflections, those always happen when you have specifically multiplication by a negative. I guess it could be division too, but usually we see multiplication. So this is multiplication division like by a number, so something that's not 1. So it actually does affect it. You can have, again, outside changes or inside changes. So if the change is on the outside, then what happens is you get a stretch vertically if your A is large, or a shrink vertically if your A is small, so you get a compression. Now, how can you find these? You just multiply your Y values by A. If your change is on the inside, you get a change horizontally, so it's a shrink if this value is big, so it compresses it inward, or you get a stretch if the value is small, so it kind of widens it. And you can find the new points by dividing the x values by that number. So again, the inside changes are kind of weird. You're not actually multiplying, you're actually dividing by that inside change. So it's something to watch out for. All right, so I'm going to just recreate the graph here. So instead of using a parent function that we're used to, sometimes you'll just use a different starting function, and they're going to give it to us here. So this is from your text. So we have the point. I'm going to make a little table here. -5, 0 is the first point. The second point is -2, 2. The third point is 0, 0. Your fourth point is 2, -4. And then your last point is 4, 0. And it looks like this. So these lines are straight, like a triangle kind of, and then this is more U-shaped. So this is our parent function. All right, I'm not going to redraw the parent function here, but we'll use it. So again, I'm going to do 2 of these changes here. So the first one, notice how it is an outside change. Right, you have that 2 on the outside. Outside changes are the easier ones. All you're going to do is multiply your Y values by whatever this is. So in this case, it's 2. So I take my original data, the X values stay the same, but the Y values are going to get multiplied by 2. So they become 0. 2 times 2 is 4. 0. -4 times 2 is -8. And the shape is going to stay the same. So let's see, I have -5, 0, -2, 4, 0, 0, 2, -8, and 4, 0. So on the left side, again, they'll be straight for those triangle piece, and then U-shape. So you can see you have this vertical stretch here, right? Let's see if I can move that a little bit. So you can see that this graph got stretched vertically, and that's because we're multiplying by a value that's larger. It's not a fraction. A fraction would kind of shrink that. Here we have an inside change, so that 2 is inside something. It's being multiplied, so what you actually do for inside changes when you're multiplying is you divide your x's by whatever this is, so in this case, by 2. So I'm going to go back to my parent function here. The y values are going to stay the same, but the x values are all going to get divided by 2. So -5 gets divided by 2. That's -2.5 or -2.5. Negative 2 becomes negative 1. 0 divided by 2 is 0. 2 divided by 2 is 1. And 4 divided by 2 is 2. So I have, let's see, negative 2.5, 0. Negative 1, 2, 0, 0. 1, negative 4, and 2, 0. And again, I'm keeping the same shape, so pointy on the left, kind of curved on the right. And you can see that this graph got compressed inward, right? It got like squished. So we have a horizontal compression here or a horizontal shrinkage. So that's the change that's happening. Now, the last example I have here is we're going to use the same parent function to start, but we're going to apply more than one change. I probably should have provided you a couple different grids here because it may get a little bit messy, but I'm just going to take it one piece at a time. And the big thing to note here is that you want to do this like you're doing order of operations. So we tend to work inside to outside. The big thing is that the order is not that big of a deal, but vertical shifts have to always go last. If you do your vertical shift first, it will mess everything else up. So you do need to do that vertical shift at the very end. So I'm going to start kind of inside to outside, and I'll come back to that +1 at the end. So I'm doing the same parent function, and again, I'm just going to do one little thing at a time here. So I have a -3. I also have this multiplier on the outside here by 2. Actually, I'm going to rewrite my parent function down here to start. So our original points are -5, 0, -2, 2, 0, 0, 2, -4, and 4, 0. All right, so I'm going to work inner to outer. I'm going to start inside here. So I see I have a -3. That's an inside change, right? So you want to go back to your notes and remember that subtraction in addition, but subtraction is a shift. So we're going to be moving this to the left or right, and we just have to think about, well, which way we're going. Subtraction here on the inside is actually a right shift. So we're going to shift everything to the right by 3 units. So if I start with my parent function, and I'm going to shift them all to the right 3 units. So I'm just going to count. 1, 2, 3, 1, 2, 3, 1, 2, 3. And again, as I'm doing that, I'm not changing the shape. 1, 2, 3, and 1, 2, 3. And everything moves over. Now, I don't normally do a table for shifts, but because I have so many steps, I am going to do a table here. So notice what happens is all these x values got moved to the right. So instead of being at -5, it's at -2. Instead of being at -2, it's at 1. Instead of being at 0, it's now at 3. Instead of being at 2, it's now at 5. And instead of being at 4, it's now at 7. All right, the next thing I'm going to do is I'm going to actually do this piece next. Now, there's actually two things going on here. I have a negative and I have a multiplier, but I can do them at the same time. It's an outside change. So it all affects the y values here. It all affects things vertically. And what I can do is multiply all the y's by -2. So instead of doing these two things separately, because I do have a reflection and I do have a multiplier here, I'm going to do them together. So my x values are not changing here. They're staying the same. But the y values are going to get multiplied by -2. So this becomes -4, and this becomes +8. So let's see. I have -2, 0. I have 1, -1, 2, 3, 4. I have 1, 2, 3, 0. I have 5, 8. and then I have 7, 0. So notice what happened here. Again, there were two changes. That negative is the flipping action, so that's why this flipped from bottom to up. And then the 2 is that stretching action. They're both affecting the y values because they're outside changes, so they're vertical changes. And then the last thing I'm going to do is that +1. It's also an outside change, so it's going to affect things vertically. And again, addition is a shift. So basically, we're going to shift it all up 1 unit. Now, I know all my transformations by heart, so if you don't, you can go back and look at the notes on these couple pages and to see which kind of changes we're looking at. Remember, addition and subtraction are always shifts. Multiplication by number is some sort of stretch or compression, and then those negatives are some sort of flipping action. So we can start that way by using, the general ideas there. So now I'm going to take my last function and just shift everything up 1 unit. So this is going to go up to here, 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 and here. And again, I know this is really tough to see, so the blue is my final answer. If I want to rewrite my table, I can. So if you think about this, the y values are shifting up. So there's no change to the x's, but everything's going to go up 1 unit here. So this went to 1, -3, 1, 9, and 1. So this is our final piece. And we just take them one little step at a time. Again, work inside to outside. Vertical shift should always be the last thing you do if you have more than one change. These definitely take some practice. So this is a good topic to maybe make a little index card for, or a little kind of cheat sheet as you're doing your homework. You may find that helpful if you find you're mixing the transformations up. And again, practice the 1-step or 2-step problems first before you get into the one like we did at the end that had multiple steps in one. The last topic we're going to do here is variation. So variation is the examples we're going to do here are a special kind of linear function, actually. To start, you can do other things as well. So we can do curves and things like that too. So we'll start with linear and then we'll kind of go from there. And a lot of you may have seen this maybe in high school as proportionality as the beginning idea of variation. So there's different types of variation. The one that we're going to start with is called direct variation. You can also say that y varies directly as x, or that y is directly proportional to x. The multiplier here, this k, is going to be a constant. It's going to be a number. That's called the variation constant or constant of proportionality. So with direct variation, what happens is x and y change together. So as x increases, y also increases. It's a similar idea to a positive slope. They increase together. So let's find the variation constant, that's the k value, in an equation in which y varies directly as x. So when you see varies directly, like we do here, so when you see direct variation or varies directly, etc., you're using the starting formula of y equals k times x. And again, k is positive, a positive number. So if I see direct variation, I'm going to just start with that basic setup. And then they'll give you enough information to actually solve for k. So notice here we're told that when y is 32, x is 2. So I can plug that in. Plug in y is 32 and plug in x is 2. Now this looks kind of funny. You can also rewrite it like this. And then you can solve. If I divide by 2 on both sides, I get k is 16. So this is the variation constant. And then for the equation, we just plug it back in, right? This is the starting equation. So you just plug in your k, and that's it. There's also indirect or inverse variation. And then in that case, what's happening is you have this division where x is in the denominator instead. So you'll hear inverse variation, y varies inversely, y is inversely proportional. K is still called the same thing, so it's still the variation constant here. So as we go through these, there is a process that you want to do. So the first thing you need to figure out is your base formula. So there's two key words that we've had is when you see something like directly, you want to think about k as a multiplier there with x. And when you hear inversely, or sometimes I'll say indirectly, you want to think about x being in the denominator. So let's read through this one. The time t required to fill a swimming pool varies inversely as the rate of flow r of water into the pool. All right, so I'm seeing inversely, which means that my formula looks something like this. Now, I'm not using y and x here. I'm using t, and I'm using r for flow. So I am going to switch out the variables. And instead of doing y and x, I'm going to do t and r. But it's the same sort of setup where the variable here is in the denominator and k is the number, it's up top. Now, once you have that, you should have enough information where you can plug in the values given to solve for k. So once you have your basic setup, your next step is, okay, well, figure out your values and let's find k. A tank truck can fill a pool in 90 minutes at a rate of 1,500 liters per minute. So what I'm told here is that when t is 90, the rate is 1,500. So there's a pair of data that goes together here. I'm going to go ahead and fill this in. So my t is 90, my r is 1,500. How do we solve this? We can multiply both sides by 1,500. And I get that k is equal to 135,000. All right, our last step here is to rewrite the equation with k, and if we need to, use it to answer any questions still. So my original equation was t equals k over r. I know my k value is 135,000. So here is my new equation. And then I do have a longer problem here. It says, how long would it take to fill the pool at a rate of 1,800 liters per minute? So I know that r is 1,800, but I'm trying to find the time here. So I can plug in my r value of 1,800. I can go ahead and use my calculator and divide this, and I get 75. Now remember, t was in minutes here, so it would take 75 minutes to fill the pool at a rate of 1,800 liters per minute. Students tend to have a really hard time with this section, so I really want you to remember these steps here. So think about what your base formula is. Use those keywords. Does it say direct or does it say inverse? It's easy to miss. You should have enough information to solve for k, and then rewrite your equation and use it to answer any other questions that still remain. Now, in our last example here, it does get more complicated, of course, it always does. So we can keep playing with this idea of variation. So we can say things that y varies directly as the nth power of k. So we can bring in squares and cubes and etc. here. And you can do the same thing with inversely, right? That power could be in the denominator instead. We also use the word jointly sometimes, which just means directly if we're doing it from more than one variable. So instead of saying that y varies directly with x and also directly with z, we just say that it varies jointly, and that word directly is implied there. So when you think about direct variation, really think about multiplying, whereas when you think about inverse variation, right, there's some sort of division going on there. So let's find an equation in which y varies jointly as x and z. So jointly is another word to think about as directly applying. Inversely, which is dividing as the square of w. All right, so let's take our time. So I know it's going to be y equals, there's always a k, so you need to have your constant. Jointly as x and z. So jointly just means directly, so we're just multiplying with x and z here. Inversely is the division part. So this piece has to go in the bottom as the square of w. That means w squared. It doesn't mean the square root. It would say root in there. So w squared. And this is our base formula. Now I'm going to plug in my information. So I know some values here. So when y is 105, x is 3, z is 20, and w is 2. So 3 times 20 is 60, so I have 60k. 2 squared is 4, and 60 divided by 4 is 15. So I can simplify this equation. I can divide both sides by 15, and I get that k is 7. So I'm able to find my k, and then remember the last step is to rewrite. So our formula is y equals, the k is 7, x z over w squared. Now here our question was to only find an equation, so I don't have to do anything else, and I'm done. But if I had other things to solve for, I could keep going and now use my equation. So the big thing is to just watch out for those keywords. Directly and jointly are both straight multipliers. Inversely is the dividing one. So be careful. This is always missed on the quizzes. This is where students make mistakes. So watch out for those that are indirect or inverse variation. And then just take your time. So they have 3 steps to find the equation. All right, so that's our lecture for today. It's a lot to cover. We cover 3 sections, and they're all pretty heavy sections. If you have questions, make sure to send me a message. Don't forget, too, that our video is only about an hour long. It's not enough to get every little detail. So I strongly encourage you to also go in and read your text. So read these sections. Look at the other examples that we did not cover. There are a lot of examples in the text that we didn't cover today. And then also don't forget you have your My Math Lab videos as well. So if you need some extra video resources, you can go ahead and watch the My Math Lab videos through our course home button in the My Math Lab feature as well. All right, I'll see you guys next time.